Welcome to the Samosa, Spectrahedra, Geometry, and Semidefinite Programming. The Samosa is the three-dimensional elliptope, the set of jointly valid correlation triples for three standardized variables. Our central theme is that one matrix supports statistical, geometric, algebraic, spectral, and algorithmic viewpoints. Why are spectrahedra useful? A single positive semidefinite constraint acts as a modeling language, a geometric description, and a computational framework. It encodes infinitely many directional inequalities, defines a convex feasible set, and becomes a semidefinite program when we add a linear objective. The lecture follows one affine matrix pencil. We begin with the positive semidefinite cone, fix the diagonal to 1, and obtain the Samosa. The determinant reveals the Cayley cubic, rank classifies the interior and boundary, and the same elliptope later provides a convex relaxation of sign matrices. A symmetric matrix is positive semidefinite when every quadratic form is non-negative. Equivalently, all eigenvalues and all principal minors are non-negative. The matrix factors as BB transpose, and it is a Gram matrix. The minimum eigenvalue is positive in the interior, 0 on the boundary, and negative outside. Now consider the construction. A symmetric 3x3 matrix belongs to a six-dimensional matrix space. Fixing its three diagonal entries to 1 creates a three-dimensional affine matrix pencil. Intersecting this affine family with the positive semidefinite cone produces the Samosa, a nonlinear but convex coordinate body. Statistically, x, y, and z are pairwise correlations. Each value may lie between -1 and 1, yet the triple can still be impossible. Positive semidefiniteness guarantees non-negative variance for every linear combination, while the determinant inequality supplies the missing three-way consistency. The principal minors make the geometry explicit. The 1x1 minors give unit normalization, and the 2x2 minors create the outer cube. The full determinant, 1 plus 2x yz minus x squared minus y squared minus z squared, carves the curved Samosa from that cube. Setting the determinant to 0 gives the Cayley cubic, the algebraic rank loss surface. The complete cubic includes non-positive semidefinite branches and complete affine lines. Positive semidefiniteness selects the bounded convex component, with 4 singular rank 1 nodes and 6 bounded seams. The three-dimensional Samosa is rank stratified. Green represents the rank 3 positive definite interior. Gold represents the rank 2 curved skin and straight seams. Red represents 4 rank 1 nodes. Convexity comes from the matrix inequality, while the cubic determinant only describes the algebraic boundary. The lower rank skeleton has tetrahedral combinatorics, 4 nodes and 6 connecting seams. Along the prototype seam 1, S, two matrix rows coincide, so a fixed null direction appears. The seam interior has rank 2, while its endpoints at S equal to plus or minus 1 have rank 1. The boundary forms through eigenvalue collapse. As the minimum eigenvalue approaches 0, the determinant and Gram volume shrink, the matrix becomes ill-conditioned, and the Gram vectors become nearly coplanar. At the boundary, a null direction appears and the rank drops from 3 to 2. For optimization, lift a sign vector to x equal to S transpose. The exact model has positive semidefiniteness, unit diagonal, and rank 1. Dropping only rank 1 gives the convex elliptope. Factorization and random hyperplane rounding then recover a feasible sign vector together with an optimization bound. The same positive semidefinite geometry appears in many fields. Lyapunov matrices certify stability in control, gram, and moment matrices certify polynomial non-negativity, covariance, density, and kernel matrices enforce valid statistical, quantum, and feature space models, and lifted matrices provide convex relaxations in combinatorial optimization. We conclude with one matrix and many viewpoints. The Samosa is a correlation body, a spectrahedron, a positive semidefinite selected cubic component, a rank stratified gram space, and a semidefinite programming prototype. The matrix never changed. Only the question asked of the matrix changed.